This is a nice simple example of how you can use integration to work on a physical problem, a physical application. So let's say that we've got a tree house and it's got this nice patio deck. And let's say we've got a nice thick jungle vine hanging from that deck. And for purposes of efficiency and future planning, we want to know how much work does it take to pull that vine up to the deck. So we'll need to know some stuff about the vine. Let's say it's 10 meters long. And let's say that the density is uniform all the way throughout the vine. So at every point of the vine, it's basically the same density, so the same amount of weight per length. Let's say it's 50 kilograms. So then for each meter of that vine, you've got 5 kilograms. So we'll say the linear density is 5 kilograms per meter. And we want to calculate how much work is done. You might try to approximate this by just saying, well, let's just allow all of the weight to be down at the bottom of the vine. Think of it that way. So kind of like a weightless string with all the weight at the bottom, because we know that we can calculate work by just doing force times distance. Distance then would be 10 meters. That's the distance you'd be pulling the weight. The force is mass times acceleration. So if the entire mass is 50 kilograms and the acceleration is 9.8 meters per second squared, we've got 50 times 9.8 times 10. If that 9.8 was 10, then we would have 5,000. So this is going to be about 5,000 joules. That would be an okay approximation, a very rough approximation. But we could get a better approximation by cutting that vine into 2 pieces and letting the entire weight of the top half hang right in the middle, and then the entire weight of the bottom half hang down at the bottom. So if we did it this way to get a better approximation, then we would just add up the work done on the top piece plus the work done on the bottom piece. So for the top piece, when we look at mass times acceleration, the mass is half of the entire mass, so 25, and then acceleration is 9.8. And then the distance for that top half, if we're letting the mass be sort of at the bottom of that top half, then the distance is only going to be 5 meters this time. So 25 times 9.8 times 5, plus, and then for the second piece, the mass is 25, the acceleration is 9.8, and then the distance there is 10. So if we used 10 instead of 9.8 for the acceleration, then we would have, so if we used 10 for the acceleration instead of 9.8, then we would have 25 times 10 times 5. 25 times 5 is 125. So times 10 is 1,250. And then for the second piece, we'd have 25 times 10 times 10. So that's 2,500. You add those together, you get 3,750 joules. That's a better approximation to the actual work than the 5,000 joules was. It's still pretty rough though. We could keep getting better and better approximations by cutting the vine up into smaller and smaller pieces. We're basically going to do that, but I want to do it in a general way because the more pieces you use, the better your approximation is. But I'm really not interested in just an approximation. I want to get the exact answer. So those approximations are getting better and better and better and better, closer and closer to some specific number that represents the actual work done. The way to get the actual work is to first set up a general situation where you're adding up the work done on a certain number of pieces, let's say n pieces, and then you let that number of pieces go to infinity. You're limiting to the exact amount of work done. So let's do that. The general situation, we take the vine, we break it up into n pieces, and we'll basically think about it as being on a y-axis. If I take my ith piece, let's say I'm going from the bottom to the top, and I just grab a random piece, we'll call it the ith piece, just as a placeholder. I want to find the work done on that ith piece. So I need force times distance. The distance done on that ith piece is going to have to do with whatever the y value is of the point that we're using. So let's call that y value y sub I. If you look at the distance that this piece will have to be pulled up, the entire length of the vine is 10. So the amount that you actually have to pull it up is going to be 10 minus y sub I. So that will be the distance. And then to get the force, again, we're doing mass times acceleration. Acceleration is 9.8. The mass is, well, we have to know what the length of our little piece is. And we're cutting this thing up into n equal pieces, and the whole length is 10. So each piece has a length of 10 divided by n. We're going to let n go to infinity. And we've been working, well, I'm assuming that you've been working with integrals. So instead of calling it 10 over n, I'm going to call it delta y, the change in y. And then as we have more pieces that we're using, that change in y is shrinking down to 0. So eventually we'll take the limit as that delta y shrinks down to 0. Mass times acceleration, the mass is the linear density times the length of the piece. Linear density was 5 kilograms per meter. So the mass is going to be 5 times the length delta y. So as we add up the work done on these n pieces, we're just adding up 5 times delta y, and then the acceleration was 9.8, and then we're multiplying that force times the distance of 10 minus y. And we're using this summation sign. Remember, it's just a nice fancy way of saying that we're adding stuff up that follows a pattern. And then we recognize that this is just a Riemann sum, and when you take the limit, it just goes to an integral. So we can write out the integral nicely. And the fundamental theorem of calculus tells us it's pretty easy to evaluate this. So we'll just write the integral. It will go from y equals 0 up to y equals 10. The delta y becomes dy. The yi becomes just y. And then we got these constants out in front. The 5 times 9.8, we can pull that out in front. 5 times 9.8 is 49. And then we're just integrating 10 minus y. So to finish it up, antiderivative is 10y minus 1/2 y squared. Plug in the endpoints, 10 and 0. When you plug in 10, you get 100 minus 1/2 of 100. So that's 100 minus 50 is 50. And then when you plug in the zeros into both places, you get 0. So we've got 49 times 50. I know that 50 times 50 would be 2,500. So I need 50 less than that. So the exact amount of work done would be 2,450 joules. This was a fairly complicated problem if you don't know calculus, but the fundamental theorem of calculus allows you to turn this into a pretty simple problem. And you can see 2,450 is going to be much more accurate. Well, it's very precise, but it's a lot better to use that number than the rough estimation we had at first of 5,000 joules.